Hi, y'all. Today we are going to talk about topic 6.5 in your packet, which is all about math. So thus far, we've talked about how to identify an equilibrium reaction, how to talk about all the different parts of an equilibrium reaction, what equilibrium actually means, and then about Le Chatelier's principle about how to force a reaction in equilibrium to shift towards the products or towards the reactants. And so now what we're going to talk about is how to calculate equilibrium concentrations from beginning concentrations, or if we have concentrations, being able to calculate the equilibrium constant K. So we've got a procedure for doing this. The procedure I am going to teach you is called using ICE charts. There are several other different ways to do this. If you're looking around on the internet, there's going to be other ways to solve these problems, but this is the way that I like the most. I think it's the most straightforward. So that's what we're going to hang with in class. If you like another way better and you want to do your work that way, that's totally fine. So no matter what, anytime we do one of these problems, these first 4 steps need to happen. So we need to make sure we have a balanced equation. We need to make sure that we know what the equilibrium expression is, writing that products over reactants. We need to identify initial concentrations for reactants and products if applicable. And if we have concentrations of both reactants and products to begin with, we're going to need to calculate our Q value to decide, are we going to shift to the left or are we going to shift to the right? Once we have that information, we can use this ICE chart. So ICE stands for initial change and equilibrium. We'll be able to identify how much that concentration is going to change in order to come to equilibrium. And then we can plug those values back into the equilibrium expression, either to solve for the concentrations or to solve for the equilibrium constant. So there's 2 examples sort of step-by-step written out in your packet as notes. So we're going to go over these 2 examples. So example number 1 says, synthesis of hydrogen fluoride from hydrogen and fluorine, assuming they're all gases, has an equilibrium constant equal to 115. In a particular experiment, 3 moles of hydrogen, 3 moles of fluorine, and 3 moles of hydrogen fluoride are placed in a 1.5 liter flask. Calculate the equilibrium concentration of all species. So they want us to find concentration at equilibrium. So again, first thing we need a balanced equation. We are synthesizing hydrogen fluoride from hydrogen and fluorine. So from hydrogen and fluorine, we are going to make hydrogen fluoride. Now, because I know I'm talking about equilibrium, I put a double-sided arrow. In order to balance it, I needed 2 in front of that HF. Step 2, they tell us that all of them are gases also. So we know what phase everything is. If they're all gases, they're all going to go in our equilibrium expression. To write the equilibrium expression, remember we take products over reactants. We're talking concentrations in this case because they're giving us moles and liters. So products over reactants, I got HF as my product. That's going to be squared because it's got a coefficient of 2. Hydrogen and fluorine both have coefficients of 1. We need to figure out what the initial concentrations are. So all of these, we have 3 moles in a 1.5 liter flask. So all of these are going to have the same concentration. 3 moles in a 1.5 liter flask. So that means we have 2, keep sig figs going, we have 2 molar solutions for everything. Next, we need to solve for our Q to see which direction our reaction is going to shift. Because we have concentrations of both our reactants and our product, we're not sure exactly which direction this is going to go. So to solve for Q, equilibrium expression is the same for Q as it is for K. We plug our concentrations in here. So 2 molar HF, 2 molar hydrogen, and 2 molar fluorine comes out to be a Q of 1. So the problem told us that our equilibrium constant for this particular reaction at this particular temperature was 115. So Q ends up being much smaller than K, which means Q is telling us that we do not have enough products to be at equilibrium. We have too many reactants. So in order to come to equilibrium, we need to shift our reaction to the right. So if we shift to the right, we are going to make more products and use up our reactants. So we are going to use that information to calculate our equilibrium concentrations. So this top graph or this top data table is sort of collecting all of that information. We have our initial concentrations of all of these things. Based on the stoichiometry of the reaction, we know that we need to be adding to our products, which means we're going to use up our reactants. So we're going to have subtraction from our reactants and addition to our products. And we don't know how much it's going to change yet. This is our variable, but we do know that they need to change based on their stoichiometry. So since hydrogen and fluorine both have a coefficient of 1, they're going to lose X. Since hydrofluoric acid has a coefficient of 2, it is going to gain 2X. So overall, we have where our concentration should be when we come to equilibrium. We just don't know what that X value is yet. So we are going to sort of rearrange those values a little bit and set up an ICE chart. So that's what we have down here in step 5. Again, ICE, remember, stands for initial change in equilibrium. This is how I usually set them up. I write my balanced equation up above, and then I write all of the information under each chemical. So hydrogen starts off with 2 molar, fluorine starts off with 2 molar, hydrofluoric acid starts off with 2 molar. Both hydrogen and fluorine are going to lose X, 1X. HF is going to gain 2X. It's 2X because of that coefficient of 2. So the equilibrium, I sum those up. Hydrogen's equilibrium concentration is going to be 2 molar minus X. Fluorine's concentration at equilibrium is going to be 2 molar minus X. And hydrofluoric acid's concentration at equilibrium is going to be 2 molar plus 2X. So I can take these equilibrium values, plug them into my equilibrium expression, my K expression, and I can solve for X. So we know that my K net value is 115. I plug my equilibrium concentrations in. I can see that I've got squared over squared. So I can simplify that down by taking the square root of both sides. This is where all of your algebra skills are going to come in handy. From that, then we can rearrange with algebra a little bit and solve for X. We get an X value of 1.528, which means that we can calculate the concentration for each of those reactants at equilibrium. So hydrogen and fluorine, they're going to have the same concentrations because their math was the same, 2 molar minus X. So 2 molar minus 1.528 gives me 0.472 molar. And then the hydrofluoric acid is going to be 2 plus 2X, gives me a molarity of a little over 5. So at equilibrium, this is what these concentrations are going to be. So hydrogen and fluorine, my reactants got used up. I made more hydrofluoric acid. Now, I should be able to plug these values back into K to verify that it does come out to be 115. That's a fantastic way to check and make sure that your math worked out the correct way. So here's another example. This one's going to be a little bit different, so we'll see how this works. Synthesis of hydrogen gas and nitrogen gas from ammonia. So to write out the equilibrium expression, we are starting with ammonia. Double-sided arrow because I'm in equilibrium to make hydrogen gas and nitrogen gas. To balance this guy, I need a 2 there and a 3 there. Initial concentration says I have 2.75 moles of ammonia mixed in a 1 liter flask. So 2.75 moles per 1 liter gives me 2.75 molar. Now it doesn't tell me I start with any hydrogen or nitrogen. And this is pretty common to start with none of your products, just to put the reactants in and have that reaction go. So I am starting off with none of my hydrogen and nitrogen, none of my products. I wrote things in the wrong place, didn't I? So there's my balanced equation. I also need my equilibrium expression from that. They tell me these are all gases. So I'm going to have hydrogen cubed, nitrogen, and then ammonia squared. In this case, I don't need to calculate Q. If I have a 0 in my reaction, I know that since that is a giant hole, my reaction is going to try to come to equilibrium to make whatever that substance is that has 0 concentration. So I know automatically that this reaction is going to shift towards those products. I don't need to find a Q. My Q basically wouldn't exist. It'd be 0. So I know that that's going to be smaller than my given K. Here's my ice chart. Again, there's my balanced equation. Initial concentration of ammonia, initial concentration of hydrogen and nitrogen are 0. I am shifting away from my reactants and towards my products. So I got the pluses and minuses there. Because of the coefficients, ammonia is going to lose 2x. And again, because of coefficients, hydrogen is going to gain 3x and nitrogen is going to gain a single x. Find my equilibrium concentrations by adding and subtracting. Plug those equilibrium concentrations into my K expression. Now, this looks like disgusting math. That's some pretty serious polynomial quadratic-y crazy stuff, which if you got your graphing calculator, you are more than welcome to plug that into your graphing calculator and solve that sucker for x. I don't know how to do that. I don't want to know how to do that because there is a shortcut. We have this thing called the 5% rule. If we look at these numbers, whatever x is, because k is so small, whatever I solve x out for is going to be really small. And when I subtract it away from the 2.75, it's not going to make that big of a difference towards my answer. Probably it's going to be times 10 to the negative 2 or 3. And so by the time I subtract it, my answer is still going to be about 2.75. So we can make an assumption that anytime we are adding or subtracting an x, we can drop that x out of our math, just to make our math a little bit easier. I have never seen an AP question that didn't allow you to be able to do this if it was necessary. Now in class, we'll go over some problems where maybe we don't need to drop out that x, or the problem before this where we could take the square root of both sides. We didn't need to drop out those x's. So there's times where we don't have to, but here, otherwise it's going to be gross math. Now, these multiplied x's on the numerator, we got to keep those. This only allows us to estimate away an added x or a subtracted x. So using that 5% rule, we simplify our math a little bit. So we're going to get, we're missing some parentheses. This is parentheses 3x cubed. So 3x parentheses cubed is going to be 9x cubed times x over whatever 2.75 squared is. 2.75 squared is 7.5625 equals 5.78 times 10 to the negative 5. Now we can rearrange that to, this says squared, it should say cubed. We can rearrange that equation using some algebra to solve for x. We get that x is 0.0634. Now, when we plug that x back into our ice chart to find my equilibrium concentrations, when I used my 5% rule, I dropped this minus 2x out of my math, which means that I'm also going to drop it out of my equilibrium expression up here. So that concentration of ammonia is going to stay 2.75. Now, if I actually went ahead and subtracted that value away, 2.75 minus 0.0634, I get 2. I get 2.68, 2.69 basically. What we're saying is that small difference in my concentration is less than 5% of my total answer. So I'm not going to worry about it too much. But again, on the multiplied numbers, I am still going to use that to help me find my concentration. So hydrogen was 3x. So 3 times 0.0634 gives me a concentration of hydrogen. Nitrogen is just 1x. So that's 0.0634. And then my concentration of ammonia. Another way that we could do this kind of problem would be where they give you the equilibrium concentrations so that you already know X and ask you to find the value for K. Same process, just with a different variable. So this idea of ice charts is going to be really important all the way through pretty much all the rest of the material that we're going to cover this year in AP Chemistry. Next semester, when we talk about acids and bases, we're going to have acid-base equilibrium. So we're going to be using the same idea. We're going to bring thermodynamics into this about heat transfers. And so not only can we figure out concentrations, but we'll be able to figure out how equilibrium affects heat. We've already been talking about that a little bit with Le Chatelier's principle. And when we talk about electrochemistry, about the flow of electrons and oxidizing and reducing different chemicals, again, those chemicals can come to equilibrium. We're still going to be talking about equilibrium constants and how that all works. So this is a really important problem-solving method that I want to make sure that we can practice now and be able to use in the future. Again, bunch of example problems after this. Try those out. The answer key is up on Schoology. And as always, let me know if you need help, and I will talk to you all later.